Okay. For the sampling distribution, we really should talk about three different types of distributions so we can understand what the sampling distribution is. So, the first distribution we have is the population distribution, and that is every possible data value that we're considering. So, if we're considering all male heights, then that would be every male in the entire population. So, maybe the United States of America is our entire population. So every male height in the entire population. And we would average all of those 170 million or however many we have together. And that would be our mean. And then the standard deviation of those numbers, 160, 70 million or so, what that would be our standard deviation. Now, let's suppose we have a sample of 1,000 males, a random sample of 1,000 males. That random sample of 1,000 males, we would average it, and that would get our X bar. So that's just like one tiny sample, like this little green piece here. That would be one sample. We can call it a sample distribution, or we can call it a data distribution. But it's not the sampling distribution. So that's one sample, it's X bar and S. Now, Chapter 7 deals with the sampling distribution, LING, is very different from the sample distribution because it's got more data values than the 160 million plus or whatever. It's got more data values usually. It depends on it depends on the population size and the sample size. But almost always the sampling distribution is much, much larger than even the population distribution. And the population distribution is much, much larger than the data distribution. So what is the sampling distribution? It takes every possible sample of size 1,000, and there are a cajillion of those, and cajillion's not a real word, but literally, if you change one number in the 1,000, then you would get a different data set. If you change two numbers in the 1,000, then you would get a completely different data set. So there would be like almost 160 million ways to change just one number in the 1,000. And then to change two numbers, it would just be exponentially more if you did every possible set of 1,000. And we take all of those X bars. So the sampling distribution is really the distribution of X bars. And so there are not infinitely many X bars, but there are just tons and tons and tons more than the population distribution. And so this distribution is the distribution of X bars, and it turns out it has exactly the same mean as the population distribution. It has a different standard deviation. We actually get a narrower standard deviation the larger our sample size. If our sample size was 1, if we were taking one data value at a time, we would have exactly the same thing as the population distribution. And this would be sigma divided by square root of 1. Square root of 1 is 1. Sigma divided by 1 is sigma. So we would have exactly the same distribution, mu and sigma, if we only took one data value at a time. Because that's really what the population distribution is. But if we take 10 data values at a time or 1,000 data values at a time, we're going to end up with a much different distribution. It'll be much narrower because the more data values that we have in our sample, the closer it is to be, and that's kind of the law of large numbers, to the true mean. The closer we are to get to the true mean, the more data values that we have. And so here are the formulas that are on the formula card for this chapter. And what this means is that the mean of all these X bars, when you average them all out, they're going to end up being your population mean. So it's saying the sampling distribution, and the sampling distribution is the distribution of X bars. And that's why when it talks about the sampling distribution, it says, hey, this is the mean of X bars, so that you don't confuse it. That's another way of just saying the mean of the sampling distribution of sample means. So that you know, hey, specifically I'm not talking about the population mean mu, but it is equal to the population mean mu. Here, sigma of subscript X bar is not actually the population standard deviation, though. You have to do a little work with it. And if you don't know the standard deviation of the population, you can estimate it with S, is what that's saying. But ideally, we want this one if we know it. So those are the two formulas, and again, that's based off this distribution. That's the mean of this distribution is just the population mean mu, and the standard deviation of this distribution. So that's just saying the same thing that this is saying. That's what these two are saying. So those are the only formulas that were given on the formula card. There is a third formula that's in your book, but it's really an adaptation of something that is under Chapter 2 on your formula card, and that's the z-score formula, the one that you were asking about. So the z-score formula on your formula card under Chapter 2 says the observed data value, and the data values are along that axis, the data value axis. And here, we don't have data values, we have x bars. So our data values for the sampling distribution are actually x bars. And so our observed data value is x bar. And then our mean of the sampling distribution is just the mean of the population distribution. And that's what this notation means. This is the mean of the regular population distribution, where an x value is just a data value. It's not a mean of data values. And likewise, this sigma x is just another way of saying sigma. So sigma x is just the standard deviation of the entire population. Here we're taking the observed value, the mean of the sampling distribution, which is also equal to this, and then the standard deviation of the sampling distribution, which is also equal to this. Now, you can ignore these subscripts of x's. You cannot ignore these subscripts of x bars, though. They actually denote the sampling distribution instead of the population distribution. But this is the population standard deviation, sigma, and this is the population mean, mu. And the way we know that this is not the population mean is this x bar tells us, hey, it's special for the sampling distribution. So hopefully now all that makes sense. This is a particular sample mean, the observed value that you're trying to find the z-score for. This is the mean of the entire population distribution. This is the standard deviation of the entire population distribution. And this is the sample size for your sample.